This work introduces a bag of prototypes dataset representation to vectorize visual datasets. It consists of 3 steps. It firstly computes a codebook composed of clustering prototypes, and then it encodes datasets as prototype histograms. When used in conjunction with Json channel divergence, the proposed descriptor is able to capture the underlying relationship across datasets. This benefit is validated by its promising results on 2 dataset-level tasks: assessing training set suitability and test set difficulty. This work develops the baseline usage of BOP scheme, and more investigations and applications will be made in the future work. Then, let's go into more details of 2 dataset-level applications. Training set suitability denotes whether a training set is suitable to train accurate models for a target dataset. Consider a scenario where we are provided with a pool of training set and a target test set. We want to select a training set to train the model and deploy the trained model onto the target set. Then the question raises, without training, how can we select the training set that will train the most accurate model for the target test set? Test set difficulty represents how challenging an unlabeled test set is for a learned model. We are given a trained model and various unlabeled test sets. We will deploy this model onto those test sets. A natural question is, how do I know the performance of the trained model on the various test environments without labels? The core of 2 dataset-level tasks is to measure the relationship between datasets. And the relationship between a pair of datasets can be simply reflected by the distance between their representations. This means, to solve 2 dataset-level tasks, we need to design an encoding method that vectorizes a dataset of images. To this end, we propose a bag of prototypes dataset representation. It consists of 3 steps. The first step is to generate a codebook. With the features of a reference dataset, we adopt standard k-means clustering algorithm to partition the feature space into k-clusters. The center of each subspace is called prototype. Then we compute the dataset histogram. For a dataset to be encoded, we project it onto the generated codebook. For each image feature, we compute its distance to all prototypes in the codebook. An image is quantized to a prototype if it has the lowest distance to it. Following the quantization, we generate a k-dimensional one-hot encoding, where the entry corresponding to the prototype is 1, and all the other entries are 0. Having computed the one-hot vectors for all image features, we sum them all and normalize it. This procedure gives us the histogram of the dataset. Lastly, we use Json channel divergence to calculate the similarity between the histogram of the reference dataset and the dataset to be encoded. Next, I'm going to introduce the experiment and the results. The first experiment is correlation study of the training set suitability. 36 different domains are considered. There are 6 unmodified domains from the original domain net, and 30 synthesized domains by using 5 different types of image transformations to 6 original domains of the domain net. And we include 2 model backbones. In this figure, we consistently observe that there are strong correlations between JS divergence of BOPs and the model classification accuracy. This means that, collaborated with JS divergence, BOP captures the similarity or dissimilarity between datasets, and thus being indicative of whether the training set will train an accurate model for the target set. We also compare BOP with other methods. We found that BOP shows strong correlation with model accuracy in other methods. This means BOP is more indicative of the training set suitability. We also studied the impacts of codebook size on the effectiveness of BOP. We observed that when the codebook size is larger than 400, BOP is stable and effective using different codebook size. We also conduct the correlation study of test set difficulty. To train the model, we use CVPR23 training set. We test whether BOP measured by JS divergence is predictive of model accuracy on test sets of CVPR23 corruption benchmark. 4 backbones are included. We consistently find that BOP strongly correlates to the classification accuracy of models. This means that BOP can well measure the difficulty of datasets for the trained model. We further studied the impact of codebook size. It can be observed that BOP remains stable and useful with different codebook size for a codebook larger than 10. Moreover, we explore the efficacy of BOP in predicting accuracy. We use BOP to train a neural regressor to predict model performance. Real-world datasets and synthetic ones are used. The model is ResNet44. In this table, we can see that BOP is superior in predicting model accuracy than other methods. Lastly, we conduct correlation study of test set difficulty under ImageNet setup. ImageNet training set is utilized to train the model. Datasets from ImageNet corruption benchmark are the test sets. We also observed that BOP has strong correlation to the model classification accuracy for different models. These results validate the effectiveness of BOP in assessing the test difficulty for the trained model. In summary, this paper introduced a bag of prototypes dataset representation, and the experiment results showed that BOP can well reflect semantic distribution of datasets. Incorporating with distance functions such as Judson channel distance, BOP captures dataset similarity. Thanks for your listening.